Good morning, everyone. A very good morning. Shall we begin the session? Yes, today's topic is a quality system with the Boolean algebra. That is how to maintain the quality, or what is a quality system that is used, and how to available or how to route the Boolean algebra that is understandable, that is used in this quality analysis, quality check, quality criteria, that is a Boolean algebra. So a logical variable that have a access, or that have x can have only one or two values or states. One is either true, one is false. So there are two values, two states, one is true, one is false, and the values are 1 and 0. True is represented by the 1 and the 0 is represented by the false. This is known as positive logic or the high true logic. Then we could also say that x equals to true equals to 0, x equals to false equals to 1. And this is known as a negative logic or the low true logic. Usually we use the positive logic convention. And electrically, 1 is represented by more positive voltage than 0, and 0 is represented by the 0 volts. Then x equals to true equals to 1 equals to 5 volts. Then x equals to false equals to 0 equals to 0. This is represented with the 0 volt, this is represented with the 1 volt, 5 volt, 0 volt, that is again represented with the true and the false. So electrically, 1 is represented by the more positive voltage than 0, and the 0 is represented by the 0 volts. And logic gates are switching circuit that perform certain simple operations on binary signals. So whatever the operation, whatever the logic gate, that is a switching circuit that performs whatever the simple operations that is used, whatever the criteria that is used on the binary signal, that is known as the logic gates. That means, yes, these are the circuit that is available for the logic gates. So the next part, what is the logic circuit? That are the switching circuits that can perform certain simple operations on the binary number, binary signals, and these operations are chosen to facilitate the implementation of a useful function. Whatever the useful function that is facilitating, whatever the useful criteria that is used, that is facilitating with the logic gate, that is facilitating with binary signals. And these operations are chosen out to facilitate the implementation of the useful function. Whatever the useful function, whatever the logic gate that is used to implement the useful functions. Then AND logic operation, this is the following circuit. This is plus minus, this is bulb, this is A and B, and this A and B, where A and B are the two, that is a closed circuit. Then next one is the AND gate. So whenever we use AND gate, that means addition of both the numbers. So this is 0, 0, output is 0. So whenever output is 1, output is 1 whenever both the inputs are 1, otherwise it remains 0. So 0, 0 is 0, 0, 1 is 0, 1, 0 is 0, 1, 1 is 1. Then AND gate, this is the symbolic representation, pictorial representation of the AND gate. This is A and B. There are two terms, there are two criteria that is coming up. So one is A, one is B. That these two inputs are going into one AND gate, then that means A into B. So this is function equals to A into B, or A multiplied B, or the A dot B. So this is A and B are the variable, and we use the dot sign to denote the AND gate. So there are two inputs, A and B, that is going into the logic. This is going into the AND gate. That means F equal, or function equals to A and B, A dot B. The next one is the AND gate. This is an example. Determine the output waveform when the input waveform A and B are applied. This is the applied waveform. This is used to represent what are the various two waveforms, that is A and B are applied over here. Next one is the OR logic operation that is used with the OR. Whenever it is true, that is closed over here. So the OR logic operation, this is A, B, one is plus minus, then bulb. So this is used for the bulb B are true. Then the OR truth table, this is A, B, A or B. This is 0, 0, 0, 0, 1, 0, 1, 0, 1, 1, 1, 1. So these are the represented with the OR truth table. This is 0, 0 and 0. That 0, 1 is 1. So whenever one of the input is 1, this becomes 1. then 1 0 1, then 1 1 is again 1. The next one is the OR gate. This is the OR gate. A and B, there are two input. This is the OR representation, that is A plus B. So these are the two variables, and denote the use of the plus to denote the ORs. The next one is a NOT truth table. That means reciprocal. Reciprocal means conversion. That means 0 becomes 1 and the 1 becomes 0. When NOT gate, this is the NOT gate. This is the representation of the circle with a NOT gate. This is A complement. Note the use of the bar over the A to denote the NOT. Sometimes a bubble is also used to indicate the inversion, like this. So this is used to indicate the inversion. There is a NOT gate. That means a bubble. Here, this is bubble is represented over the OR gate. That is NOT gate. Here, this bubble is represented over the input signal only. Now, what are the logic gates? So, in fact, it is very simpler to manufacture the combination NOT and NOT OR. Then it is to deal with the AND or AND OR. So, whatever it is possible to manufacture, it is manufactured to use a combination of the NOT AND or NOT. So, whatever the logic signal that is used to manufacture the combination of the AND NOT OR, then it is used to deal with the AND or NOT. Now, when we use the NOT AND, that becomes NAND. So, whenever I combine the NOT and the AND both, that becomes NAND. That is the NOT of the AND. Then, when it is used with the NOT and O, then it is used as a NOR. That means NOR NOR. That is NOT of OR. Then this is the NAND truth table. This is the A NAND B. That means NOT of AND. We can say that first of all we have to carry out the AND, then convert them. Why convert them? Because first of all we have to multiply both of them. For example, 0 0 becomes 0. Now the reverse, that means NAND. Reverse of the 0 is 1. Then 0 1 is 0. Reverse is 1. 1 0 is 0. Reverse is 1. But when I say 1 1, that becomes 0. Why? Because 1 1 output is, or the AND is 1 and the NOT of AND is 0. That means reciprocal of this one. This is a NOT of AND. That means this bubble is placed over here. Why this bubble? Because this is NOT of AND. AND is converted into the NOT. Then the NOT truth table. NOT truth table means NOT of OR. So first of all we are able to get the OR of A or B. That becomes 0 0 0, 0 1 0, 1 0 0, 1 1 0. So this is A nor B. That is the NOT of OR. Then 0 1 0, 1 0 0, 1 1. Why? 1 1 becomes 1, as you know, but this becomes 0 because of the NOT. Now, this is the representation. We use bubble over the OR gate. Nothing. So whenever I want to present the OR gate, so I have to write the bubble over the OR gate. That is a NOT of the OR gate. Then the exclusive OR truth table. This is A XOR B. This is A XOR B. This is AB plus AB dash. This is the XOR gate. That means this is the XOR. That means there is a OR gate and we use X over there. So we use X over there. That is a XOR gate. This is A plus plus B. Now this exclusive NOR gate truth table is NOT of X or B. This is A XOR B. AB plus AB dash. Now this is the exclusive NOR gate. This is also known as the equivalence gate. So these are the rules regulation of the Boolean algebra. These are the various rules and the statement that is available over here. Now, when we use the cumulative law, associative law, that means A into B is equals to B into A. So whenever I combine, whenever we can say use the AND operation with the A and B, that becomes the B and A. Then A plus B equals to B plus A. So operations on the Boolean variables are defined by the rules and the laws. That is the most important part of which are presented over here. One is a commutative law. One is a commutative law. That means A into B equals to B into A. Then A plus B equals to B plus A. This states that the order of the variable is very unimportant over here. Then next one is the associative law. That means A into B into C equals to A into B into C. That means B and C are associated with each other, and the B and C and the A and B are also associated with each other. So this states that the grouping of the variables is very unimportant, very unrule. That is a very much, or that is a rule at the law of the Boolean algebra. This states that the grouping of the variable is very unimportant. Why? Because there is the associative rule that is available over here. Now next one is the distributive law. That means every variable or the two operands or the two variables are operated with each other or distributed with each other, or we can say distributed among the two variables. So this is A into B plus C. That becomes A into B plus A into C. That is A into B plus A into C. That states that we can remove the parentheses by multiplying them. When we multiply, so the parentheses will be removed, parentheses will be declared. And the above laws are the same as in the ordinary algebra, where plus and the divider are interpreted as addition and the subtraction. The basic rules involving one variable, this is A plus 0 equals to AA into 0 equals to 0, A plus 1 equals to 1A into 1 equals to 1, then A plus A equals to A. And A into A is again A. Then A plus A dash, that means complement plus A equals to 1 and A plus A is 0. And it should be noted that A complement or A double complement is always A. And the informal proof of each of these rules is easily accomplished by taking the advantage of the fact that the variable can have only two possible values. For example, rule 2 says A plus 1 equals to 1, and if A equals to 0, then 0 plus 1 is 1, A equals to 1, then 1 plus 1 is 1. Then these are the some useful rules. So the theorem that is available, this is A plus AB equals to A plus A into B equals to A plus B. Why? Because this is complement, that one complement or the complement is taken out with the one another that is available with, or used with this. Then A into A plus B equals to A. Then A complement plus B equals to A into B. And these may be proved in a similar manner also. For example, when we say that A plus A into B equals to A plus B. This is AB, A complement B, A plus A complement B, then A plus B. So A complement means the negation of this. 0 becomes 1, 0 becomes 1, 1 becomes 0, 0. Then A negation into B. So we multiply the A negation or the A complement into B. That means we use the AND operation among the A and the B. So 1 0 becomes 0, 1 1 becomes 1, 0 0 becomes 0, 1 0 becomes 0. Then A plus A complement B. So A complement B we have already find out. Now we add the A with this. That means now we are going to do the OR operation with this A and the A dash B. This is 0 0 is 0, 0 1 is 1, 1 0 is 1, 1 1 is 1. Then A plus B. This is A plus B. 0 0 0, 0 1 1, 1 0 1, 1 1 is again 1. Now finally we come to the De Morgan's law, which are particularly useful when dealing with the NAND or NOR gate. They are stated as this one. This is the De Morgan's theorem. That is one of the important law as compared to the commutative law, as compared to the distributive law, associative law. This is very important. This is A plus B whole complement. Now the that is the OR operation is converted into the AND operation. So A plus B complement equals to A complement into B complement. That is rewrite not of A or B is equals to not of A and not of B. A nor B, not of A and not of B. So this is related with a not or an AND gate, and that can be extended to any number of the variable. This is A plus B plus C equals to A into B into C. This is the same. Now, this is how it works. This is A plus B, as you know. Now, I have to find out the complement of this one. Complement means this becomes 1, 0, 0, 0. Look. Now, we have to find out the A complement. Now, this is the complement of A, 1, 1, 0, 0. Now, the B complement, 1, 0, 1, 0. Now, the multiplication of these two. 1, 1 becomes 1, then 0, then 0, then 0. This is 1, 0, 0, 0. That is similar to this one. This is one of the De Morgan's law. Next law is A into B whole complement equals to A complement B plus B complement. That means this time OR becomes AND. Last time AND becomes OR, this time OR becomes AND. So now this, first of all, we have to take the A or B. That means 0, 0 becomes 0, 0 becomes 0, then 1, 0, 0, 1, 1, 1. This is A or B. Now we have to find out the complement of A or B. Then 1, 1, 1, 0. Then A complement, B complement. A complement is 1, 1, 0, 0. B complement is 1, 0, 1, 0. Then A complement plus B complement. This is the addition of these. That means we have to find out the AND over here. 1, 1 becomes 1. Then 0, 0, 0. This is the same. This is 1, 1, 1 because this is the OR operation. So 1, 1, 1, 0. So this is same as this one. This is again the next law. That is the second law. Now this is a symbolic representation. AB OR is AB and not. Then AB equals to A complement into B complement. This is again the same. And taking the NAND gate as an example, we can derive effective AND or gating, although physically we are using only one type of gate. For example, F equals to A into B plus C into D. This is A into B, this is C into D, this is A, B, C, D, A, B, C, D, A, B, C, D. Now, next is referred as a NAND gate and the NAND gating. And any logical operation may be, or any logical equation may be implemented using the NAND gates only. Therefore, the NAND gates may be regarded as a universal gates. In the question, in assignment question advisor, which is known as a universal gate, that is a NAND gate. And same is true for the NOR gate also. Next advantage of using the NAND or NOR are simplest and the cheapest to fabricate. That means it is very simple to use, very cheapest to fabricate, very cheapest to use, then fastest operating speed. The speed of this De Morgan's law, that is the NAND and the node, is very high. Then lowest power disruptions or dissipation. That means there is a lack of, or there is a lowest power dissipation. There is a loss of, or the very little power dissipation. Then the simplification of the expressions using the Boolean algebra, that is very important to minimize the Boolean functions, and this often brings about a reduction in the number of gates or the input that are needed. For example, when we consider AB plus A, B plus C plus B, B plus C. That means we are using the AND gate and the OR gate together. So in general, multiply out and collect the common terms exactly as you do when simplifying the ordinary algebraic equation. Then the expression of the problem that is solved using the Boolean algebra. So most real problems are defined using a sequential or the sentential structure, that is therefore necessary to translate such sentences into the Boolean equations if we are able to derive a digital circuit to give a Boolean result. Then these are the very example. If it will snow, equals to 1. If true, false. Cloudy, 1, false. True or cold, 1, false. Then A or B. Then the